I wish you a good morning and welcome you to the second session. First of all, I want to thank Judith and Francesca for organizing everything here. You did a great job, and it's an honor for me to host or chair the first technology session. One thing I learned taking part in this European network of digital building permits is that when we use one term, we all understand something different. Something we were talking about, the digital building logbook. Every country has some different imagination what should be in there, and therefore it's so important that we talk to each other in the session here, but also in the coffee breaks. So as an Austrian, I know how important coffee is. We will have some interesting talks now too. One thing we also imagine from a digital building permission process is that it speeds up the process. Now we're about 12 minutes delayed, so we will skip the question at the end and we'll have some question right after the talk. And we'll see if the speakers will also have to speed up their process. So, but I don't think so, because we have some really important and some very interesting talks. And it's an honor to first welcome Siham El Yamani for their talk.
Hello, everyone. I would like to start with something. This morning, while I was in the hotel, I saw the Gaudi's architecture, and while heading up to the conference, I was thinking how far he was envisioning, has the vision ages ago about the 3D building elements. Do you know that he never draws his plans in 2D. He first imagined them in 3D spatial dimension and then do the 3D building models. He took in considerations the surrounding of the building's obstacles in order to have more natural sunlight to it. It was resonating with me so deeply that ages ago he was aware of that. Since today we're gonna talk specifically about the geometrical challenges that goes into the digital permit processes, especially for the DPP. So, in order to talk about this, we will first, between lies, I'm Siham. So, and my role is to help multiple partners, municipalities, and software developers during the Czech project to implement the GeoBIM solutions that are developed within the TU Delft. We know that in order to digitalize regulations, we need the three triangle of designers, software developers, and the municipalities, which has the key success to the achievements of the project. But during the data integration and data implementation process, we know that the BIM to Geo is at the axe of tendencies and also axe of the heart of the challenges. It can be overwhelming to decide which semantical and geometrical data requirements that are needed from the BIM to IFC exchanges to the Geo city context on city JSON or on city JML files. So to address these challenges, we introduce the concept of level of information detail, which is a standard that has been introduced by Building Smart in 2021. And it was mainly to address the granularity of the data that needed to be extracted, which feature and which attribute are going to be stored into IFC in order to extract it to the GeoWorld into which class and which attribute to be stored into CDJSON. So in order to make the process less overwhelming, we will address mainly what are the geometrical information need within the Czech project for the pilot cases. And for that, we have 19 partners within the Czech projects, from software developers, municipalities, Vila Nova de Gaia, Prague, and Vila Nova de Gaia, Prague, Ascoli and Lisbon, which are the key success of the data requirement pilot case. We know exactly that we need a use case practice in order to demonstrate the process itself. So we have the standardization organization, OGC Building Smart, and one of the main researchers, universities, Minio, Brescia, Fraunhofer, and TU Delft. Software developers that are mainly included in this process of implementation, SciP and VCS. So, the key of our approach, BIM to Geo, LOEN, is mainly 3 stages. So, first, the analyze and the interpretation of the DPP regulations to decide which are the city and the building level objects that are needed during this interpretation, determine the core and what are the differences between municipalities. And believe me, which is the more challenging and overwhelming part. The second phase is to detect 5 processes technologically to help these implementations. And within the output of the conversion, we have the geometrical modeling guidelines, which are an iterative process that should go from the designers within the IFC model and back to the designers to implement these modeling guidelines during the process. So, for that, we choose last year within the Czech project, within University Brescia and Minio, to focus under the feedback of the community of practice of the project on 4 mainly regulations: distance to buildings, to sidewalks, the maximum building height and the building height within the 4 municipalities, minimum area, and the buildability index, which I need to explain more, like at the potential of a land on a building to the maximum usability, and it can be translated as a data requirement based on the ratio to area, area to area, or volume to area, and which take the maximum of usability of the building. And for that, after this stage, we detected 5 concepts and 5 solutions in order to make this process implemented. The first one is the detecting the accuracy based on the tolerances of the 4 municipalities, urban ones, in order to detect what is the level of the details geometrically that is needed as an input during this process. The georeferencing, it was made through my teammates' solutions developed with this IFC-GRF, which is a tool, which is, I will give you also the links in GitHub. And we have also a website in order that you can implement your IFC model. It supports the 4th version, the 3.2, and you can georeference it in order to have it based on the IFC map conversion to the city level. We have the building envelope extractions, which is based on the voxelization approach. It approximates the envelope of the building to its accuracy in order to extract the elements that are needed to compute buildability index and maximum building height. One of the key elements that has been checked until now are georeference accuracy, building envelope extraction, and the floor extractions. The 2 last ones are the space extractions for the minimum area facade alignments in order to say to what accuracy the overhangs are needed to be extracted to align to the data requirements of the inputs. These 2 last ones are undergoing and not yet checked on the geometry level. So I will give you the showcase that we tried to start with during the study case, which is the building height and the maximum building height. And believe me, beyond the overview of the complexities for these 4 municipalities, which is so interesting and challenging, is that we detected 4 levels of complexities. And thankfully, during the exchange with them, we could have more clarification on that. But what we detected is, for example, at the same level of municipality, you have an overlapping of applicability of the regulations. And then you found out that the maximum building height can be either defined by the maximum floor levels, or it can be defined by the computations of the lowest part, ground levels elevations, to the roof elevations. It can go beyond that in terms of complexities. Whenever you have slope terrain, the definitions, the approach is different, and whenever you have also roads, it becomes so overwhelming. We chose one simple case in this study case. We had the example of municipality of Villanova de Gaia, provided by one of our partners, which is the design architecture company, Zvei, in IFC4. We checked specifically with my teammates how far the geometry is validated For example, here we can see how far we have these elements structured for the data requirement. We need to provide IFC walls, IFC standards, how far the IFC coverings are structured not under the proxy elements, but as IFC coverings, etc. But during this process, we used the second, after the georeferencing, the building envelope extractor, based on the solutions of the tool that we provided by TU Delft. The output of the computations is the outer shells based on the voxelization approach, which is as you see, and by the end we have the modeling requirements that are given to designers. One of the challenges that we faced is, for example, IFC sites was not structured, so we couldn't have the separations during the conversions, and also IFC proxy elements with coverings which crashed the geometry during the conversion. So here you see also one challenge during this study case that was implemented is to store the georeferencing data in the output file of City JSON based on the conversion. So finally, to sum up, I don't want to say it's all rosy and glittery. We have ongoing efforts, but there are many challenges and research lessons learned. But first, on a positive way, the ongoing works is to upgrade our solutions, the converter, to include the complexity of indoors, IFC spaces, and the alignments of the facade, to also finalize the data requirement into the machine-readable format by our partner OGC, and in order to have all the data requirements-based GLOEN, assist and complete the implementations of regulations within our software partners during this process. And I will change my umbrella. Under the coordinator umbrella, we have also other problems. In order also to have more scalability, we still need to navigate the complexities and to finalize the GLOEN process. Provide more IFC model structures, which are going to be provided by our designers partners, municipalities data collections, and I will insist, which is the key to success, to get back to them and also to do a second phase of collecting the data. Last but not least, one of the lessons learned is that we need more accuracy beyond the process itself. We need to define how far the accuracy should be human and digital during the human and digital process. And we need the more practices, use cases, in order to demonstrate how far this approach is feasible or reproducible. And I think that I need to finalize with that flexibility is also the key to maximize the innovation and the digital building process. Thank you.
So thank you for keeping the time so well. Wait, we have time for one or two short questions. And one good news, Francesca was so nice to put the lunch break right after our session. So if you have more in-depth questions, you can ask the speakers right afterwards in a long time. First and then.
Okay, one question, because I think it's related for also our project. You, in this process, you said that there is a moment when you retrieve information from the urban planning. So I am asking if this information is you retrieve it from some kind of GML file or CTGML file, and then, because, for example, if we have a plot or a parcel, no, that it says, it tells us which is the square meters that we are allowed to build the building. So this information that is particular for each of the plots, how you retrieve this information and what process you select some file, because normally this information is from the municipality, no, in one, normally in GML file, at least in Spain. So you have to select information from there, how this process is performed.
Yeah, thank you so much. I need, before to answer, to address credits to many partners, because it's not an individual effort. First, we have, from the side of the data input, municipalities. We address to them directly. We have also partners that could digitalize and get more visualization of the interpretations of the regulations. So we have OGC, US, and University of Minho. We, in order to get data that are already stored in GML format, we had VCS who could retrieve and extrude this information. For example, some of the plots, they are on 2D and they need to extrude it based on the height that is existing. This is for the part of existing building, but here I'm more concerned about new buildings that are going to be implemented in the surroundings. Hopefully I answered your questions.
Yeah. Hey.
Yeah.
Pasi from Solibri. You had this space extraction thing coming, so what is that going to do? I'm a bit confused.
Oh, yes. This is like at the first brainstorming phase, mainly for the minimum area regulations, in order to know what are the minimum regulations that are prescribed by the 4 municipalities. We need to check the space. So
okay,
yeah,
IFC has spaces, so
yeah,
like, are you doing something with those spaces, or
we need to see that when the BIM is modeled, there is a lot of confusions between rooms and spaces, and in order to have an automatic extraction to IFC spaces, there has been some complexity to define what are the spaces, because there are like areas, gross areas, net areas. So these definitions of identifying what are the spaces that are required, and to have automatic extractions and checks. This is why it's needed.
Thanks.
Yeah.
So thank you again for your talk.
All the pressure.
And now I use the information Adrian gave you. Now we're going from the Netherlands to Austria and ask Simon Fischer for his talk.
For the introduction, but that's not my talk. So let me just introduce myself. I'm Simon Fischer from Austria. I'm a PhD candidate at the TU Wien, the Technical University of Vienna. And yeah, we did some, now it should come, yeah. We did some research on code compliance checking, and I want to dive into a very specific topic there. In fact, code compliance checking approaches for elements implicitly contained in building models. So this is was part of the Brise Vienna project. This was a research project by the Austrian Vienna Building Authority to develop a digital building permit process. And we also implemented a prototype of a code checking system there. But I will skip general information on Brise Vienna here because my colleague Harald is going to have a talk on that tomorrow. So let's focus on the use of implicitly contained information in building models. So elements relevant for code compliance checking usually are modeled as individual elements in building models, like we see here, walls or doors and even spaces. So, but there are also virtual elements that are not explicitly modeled, but instead they are generated from the existing information in building models, so information that's already there from other use cases. And we identified in our project escape routes and fire compartments as such elements. So what information do we have in buildings models for these two virtual elements? Of course, there is geometry and properties. There are others like relations or so, but let's just focus on these two and keep it simple. So when we have a look on escape routes, besides the geometry, a very important information is the occupancy number in spaces. Because in building regulations, normally the dimension requirements for elements along escape routes, like corridors or doors, are dependent on the summed up number of people that pass such an element, and they come from different starting positions. So it is a crucial information for escape routes, and it's usually already in building models. When you have a look at fire compartments, for us interesting is the fire resistance of the boundary elements. So in this example, we have their walls, fire resistance information on walls, and also for doors. So the interesting thing when we have these implicitly contained information, want to generate virtual elements from them, that the data allows different options. So as we can see here, this geometry allows 4 different escape routes from the left to the right. Of course, one escape route goes through a door in the wrong direction, but in some cases, if there are not too many people, this is also allowed, in Austria, for example. So when we think of a complex building with several starting positions, with several escape routes, they all have different options, so we get a lot of possible combinations of these escape routes. Then when we look at the fire compartments, I displayed here only 2 of 8 possible fire compartment configurations for this geometry, because it would overlay the image. But as you can see here, there are also many different options for this problem. And the point I want to make here is that when we use the implicitly contained information, we have different options and don't know which one is the best or which one is the intended by the planner. So let me state this formally. This is the validation of elements that are not explicitly defined in the building model, while the implicitly contained information allows different options to generate them. So this was our challenge we faced here. We discovered 3 approaches to handle this challenge. So the first one is the fully automated generation. For an iterative algorithm, it is possible to find all possible combinations. But in Austria, we have there a problem because this would represent a liability reversal. In Austria, the party that defines an element is liable for it. And we require the planner to do that. Otherwise, the building authority would be liable for it, but they only validate it. So this is very important in Austria, that the designer or the planner defines the actual course of the escape routes, or, for example, the configurations of fire compartments. The second option would be to explicitly model these elements again. But with this, we would have, on the one hand, redundant information, because the information is already in there and we still model it again. And the second one is we lose the advantage of the implicitly contained information because we don't use it. Instead, the whole planning of fire compartments and escape routes is done beforehand. So we developed a concept called generation validation. This consists of 2 automated steps, the generation and the validation, and has a manual selection in between. So the generation automatically defines or generates all possible escape routes, for example, and displays them to the planner to have a pool of possible escape routes. The planner then can select these, and in the validation, the whole network, the selected network, then is checked with the requirements the whole network has. So the width requirements on the summed up people, for example, on specific at specific places like doors or corridors. And the validation is used by the planners as self-assessment before submission, and then by the authority, by the building authority for the real validation and the permission. And by this, we have a high level of automation, and we are still legally compliant in Austria. And also, the designer planner can select something, so they are not influenced by the full automation. We implemented this concept in the Brise Vienna project as checking rules for the software Solibri Office. We implemented algorithms for indoor navigation model, pathfinding algorithms, and checking algorithms for the elements. And then we validated the approach with 16 real-world models in the pilot phase. And these are the results of 4 of them. So let's just have a quick look on the differences between the generation and the validation. Here we see the results of one of the generation. In the bottom space, you can see there are many different escape routes for just one space. And here on the right, we see the selected escape routes. And this manual selection process, as I mentioned before, is done in this concept for escape routes with an additional property in a door that references the next door. So to select escape routes, the applicant, the designer, references the next door on the escape route, and then the validation uses the same algorithms as the generation, but just from door to door, to regenerate the selected escape routes. So to sum up our results, they encourage to use implicitly contained information to generate these virtual elements. We demonstrated this concept on escape routes and fire compartments. So for these 2 use cases, it actually works. So we showed that it worked. And we consist with that with the legal framework in Austria. Last, we also provide a single source of truth because we use the implicitly contained information. So this cannot contradict with the information then on the escape routes, for example. So what is next? As I said, we demonstrated it for 2 use cases, escape routes and fire compartments. So now it's time to screen more regulations, for example, to see where this is also applicable or where this problem also, this challenge also exists. So yeah, that brings me to the end of my talk. Thank you very much, and I'm open for questions.
Simon, thank you very much. Do we have? It was immediately going up. So 1 second.
Thank you. Hey, thanks for the presentation. Quick question: you assessed here the case of fire evacuation kind of stuff.
Yeah.
Which other things have you looked at and could be implicit designs inside BIM files? You know, I can imagine what, but I think you have given a thought.
Yeah, so you mean other use cases that we can use that? Yeah. So for example, what we also worked on is the light incidents of other for rooms, for example, and then there you always have restrictions because of other buildings. Then the light incidents for a room can be restricted or so. And then here it is also the problem, which windows do you select, for example, for the light incidents? And here you also have this problem. We didn't apply this concept yet there, but we think, for example, for this, it also has potential.
Yeah. How do you model the fire compartments in IFC? Do you put some more information to the
for the fire compartments, we think fire compartments, or in the Brise Vienna project, this is a very space related information. So we have an additional property for in the space that assigns a space then to a fire compartment, and then the whole fire compartment can be regenerated from the selected space.
Thanks.
Yeah.
This was really a short question. So thank you, Simon, again. Now we go back to the Netherlands, the nice city of Rotterdam, Rolf Jonker.
Thank you. Good afternoon. Thank you for the possibility to show the space hierarchy service to you today. And my name is Rolf Jonker, and I'm working for the municipality of Rotterdam as a project leader. And what I'm showing you today is a development of the city of Rotterdam together with AAC geeks Thomas Krijne. It's a pilot project for the Dutch Environment and Planning Act. We call it in the Netherlands de Omgevingswet. And it's part of the Digital City program of Rotterdam. I will tell you why we make a space hierarchy service, how we did that, what are the results, and I will give you some print screens of the space hierarchy service that we developed. But first, why? In Rotterdam, we are working on a digital building permit service, and the space hierarchy service is developed in the context of that. And the building permit service relies on three important components. It's the BIM model given to us by a project developer. The second component is the digital city that we have as a municipality. And the third component are machine-readable legislations. And if you combine those three, then you can detect some conflicts. And we believe in Rotterdam that after we detect a conflict, that we have consultation for adjustment. We don't want a service that is like the computer says no. And then we hope we can reach appropriate design. Goals that we have on short time for the space hierarchy service is to create knowledge, to research, reach consensus on space modeling, make it human and machine readable, improve the process, and increase the job satisfaction of the modeler. And it has to contribute to the Environment and Planning Act, and these are the long-term goals of the new act. And we hope it can contribute to added value of the city of Rotterdam and residents, and hopefully ook for other cities and other organizations. So we're looking for space, and when we're looking for space in our legislations, it's referencing spatial concepts, and it's a Dutch rule, but here it's talking about the build percentage. It's a space type. It's talking about office, companies, gross floor area, habitable space, toilet room, and so on, and so on. So if we want to a machine to help us check the rule, we have to explain what these spaces are. And those spaces are sometimes in the BIM domain, but sometimes also in the GIS domain. And we hope we can exchange the knowledge with the roadmap of Building Smart and OGC, who are trying to enabling the information continuity. And I think we have a use case, so group 1 would be interesting for us, and also group 3, development of BIM GIS standards. And we made a user story of our service. So how did we work on the space standardization? What we're trying to do is to make the term like habitable zone, what is the space type, align the semantics for human-to-human communication, human-to-machine, but also to machine communication where a human is not involved anymore. And to do that, we make use of the IFC schema, the IDS, and also the it's a Dutch standardization. It's the NENS 36110. It are our GIS information models based on the OGC and W3C standards. And we also make use of the space hierarchy given to us by our standardization institutes that you see on the left side. So it's explaining what is gross floor area, what is net floor area, etc., etc. And on the right side, you see it's more like a hierarchy. What space is part of another space? So we looked up 3 theoretical buildings, detached family house, row housing, and apartment building, to detect what kind of space is inside such a building. And it's a lot. So you see site volume, but also habitable space. So we tried to standardize the type. And not only in and around the space, but also the administrative spaces. And they are mostly in the GIS domain, but sometimes also in the BIM. And what we see is that there is an ambiguity in the meaning of a space type. So when we're talking about a gross volume, it can mean different things, and that's the problem. So we classified that. So it's not an ambiguity anymore. So to reach that, we make a large model of what space types are and how they are related to each other. And here I'm showing you just a small part of the model. And if we, after that we had the space types clear, it's possible to make logic to go from space type A to space type B. And in this example, you see a living room, dining room, kitchen, office. It are habitable spaces, and we can combine them to a habitable zone. But if you look closely, you see that the non-load-bearing separating wall is part of the zone, and that's a large problem. And to create all the spaces that we need, we defined a minimal set of IFC data needed to create all the spaces I showed you. And it's a minimal set because we don't want to place a burden on our modelers that have to give the BIM models to us. So what did we do? This is an example of what we make. Thank you. We have 2 spaces and a non-separating wall in between. And you see that there's a problem because the wall can extend beyond the spaces, and there can also be a part of the wall missing because there is a door void. So we cannot use the common Boolean operation, like combine those 3 geometries, because then you get the wrong solution. So what we did was another approach developed by Thomas Kreine, where we use half spaces that is like a boundary of a space, and we're looking for the intersection of the half spaces, and then we can reach the right space as a new space type. That's an aggregation of other space types. So here you see that how it works. We have 2 spaces. It has a relation to its space boundaries, its space half space types, and so when we analyze that, we can make other spaces out of that. And the service that we make relies on a compliant model, and not all models are compliant. So what we did was an additional solution that uses voxelization to check if there is a space inside a space in the model, if there is a space modeled inside a space found by the voxelization method. So, and this is a sneak preview screenshot of how the space hierarchy service work. On the left side, you see the input model. It has a lot of spaces in it. And on the right side, you see the aggregation of the spaces. And when you want to work further on your model, you can also download it and put it back in your modeling software. So that's my presentation. Thank you.
Thank you for your perfect timing with the slides, as you said before. Are there any questions? Would have time for one question. It doesn't look like this, so I would say write a questionnaire at the lunch break. Okay. So thanks a lot. And now we go further north to the United Kingdom and ask Nick Nisbet to the floor.
Is that better? I'll say that again. I don't like software. Let me show you version 1 of the software I'll be talking about. 4 coloring pencils. And Ayad earlier gave you a preview of the software that I'll be talking about. So, he showed you a little of Raise, and I'd like just to mention why it's important for the work we're doing. It's about getting the domain experts, the regulators, to add and progressively refine and agree the markup. So we leave them in control. I believe it can be independent of language and grammar, and hopefully Arabic as well. And it's independent of the target information resources. We've seen IFC, we've seen GML being mentioned, City GML. It may not be models, it may be other databases. And if all else fails, we may have to take the information resource as the users, stop and ask them a question. So we want the domain experts to review the markup and its implications, and we're going to see a workbench which lets them do that. And we can also offer them reports and summaries, and we can play back the regulations to them in lots of different ways, so that somewhere along the line you hope that they all say yes. We can process any normative content. What do I mean by normative? I mean rules, regulations, laws, contracts, including smart contracts. And we can also do other content, dictionaries, declarative information like dictionaries and lookups and mapping tables. And of course, if we wanted to, we can also make any informative content available. Informative content is models or users or databases or whatever it happens to be. Anything that includes text, tables, links, cross-references, and increasingly I think we can handle a lot of the challenges like rule, features, scale, complexity, intensity, ambiguity, subjectivity, and the need for simulation sometimes. The end result is a no-code solution. We can actually get rid of the programmers. In fact, last month I sacked my programmer. So that's the future. We don't have to be dependent on programmers because we can stop interpreting the regulations and instead use them directly. What we can do is have a rule engine, and the workbench I'll be showing has a rule engine built in, which is smarter than most rule engines. Or if you must, you can export it to Drools or JSON or DMN or SparkQull or any of those other languages that don't quite work. So here's Raise. You saw a bit earlier, but I think if you remember anything from this, I'd like you to remember the sentence at the top. All doors or windows on the ground floor should open outwards except shop fronts. It's an example of the 4 colors, and it's a good example in the sense that it's based on English regulations, and we always treat shopkeeping as special. So we can do the markup using coloring pencils, or we can do it electronically if we need to. Then we'll see using dictionary and case files to set up the stuff we're taking to be true. In this case, that we want to test a regulation against a model. And then we'll get results, which are, of course, informative, we hope. So off we go. We log in. There's our sentence at the top. I've highlighted the first word, I've hit one of the electronic colouring pencils at the top, and I can, if I want to, fill in some extra detail, but I don't have to. I normally give it each piece of information an ID. That could be automatic. But in fact, the only thing that I do here is I say that doors means door in the singular. One of the strange things about language is that we mix up plurals and singulars all the time. Okay, so we finished the markup. And above the markup, we have something like 15 different tabs. This is why I call it a workbench. Only 3 of them are interactive, and the rest are reports and results and analysis. One of those reports is it can generate a visual program, Dynamo or Grasshopper or whatever it happens to be. So if you're really into visual programming, we can write it for you. If, on the other hand, you're a little bit more abstract, you can have a conceptual graph. This is following the work by Solehan and the Singapore regulations. Again, carry on using the same colors because I like those colors. I've been using them for 15 years now. So if you've got someone who wants to think abstract, they can see a concept graph. And of course, for real regulations, the graph can spread over, well, I'd need the whole screen, of course, for some regulations. But we can also play it back as first-order logic statements, predicate logic, propositional logic, visual programming. Oh, we've seen that. Lots of other things. Also checklists. We can play it back as a checklist, which is a dynamic checklist. So even if you haven't got a BIM or a GIS model, you can give the regulator a copy of his regulation. Okay, so next thing, we're going to do some definitive work. We're going to set up an example. We're going to have name the models that we want to test and the regulations we want to test. And we can have several models in there. We can have several regulations. And then we press, well, in this case, one of the things we can generate is all possible test cases. Now, that simple regulation with 5 metrics in it actually has about 200 and something possible test cases. I'm bone idle, so I got the machine to generate all the test cases in one model so I could check them all. So again, we can pass back and reassure people that the engine is getting the right results. So that's the model we're going to test. And it comes back saying some of these have passed, so it lists the ones that have passed. Much more excitingly, we get a list of the things that have failed, or not, sorry, next one. List of all the ones that have failed, all the way down there. If it had been successful, I would have got a certificate saying you may go ahead and build this building. But this is a notification of failures. We can also generate the explanations of what you would have to do to fix them. And that uses a technique called logical differentiation. Look it up in Wikipedia when you can't sleep. Okay, so in summary, the AEC3 Require 1 software has been tested in a project called RegBIM, which looked at one accessibility clause, the whole of BREEAM, and also a government policy called the Code for Sustainable Homes, which was actually cancelled whilst we were automating it. And that tells you something, that regulations are dynamic. They come and go, they change. We've got to be able to automate them quicker than the regulators can introduce new ones. We've used it in the DCOM digital compliance projects, where we implemented 3 of the approved documents, the regulations in the UK, on fire, energy, and accessibility. And we've also used it with the Health and Safety Executive in the UK to do live checking of health and safety on building sites. So I think the lesson about RAISE is that it abolishes programmers. We can have lots of different presentations of normative knowledge. We can manage the declarative knowledge and the dictionaries we use. Also, semantic enhancement is a kind of declaration of how you think things should be. And we can get results and explainability from informative knowledge. So we can actually tell people how to fix things if they want to. If we pass them, we can tell them what it is that passed, which they might want to protect and preserve so that they don't undo the good result that they've just got. Okay. That's it. Thank you.
Nick, thanks a lot for keeping the time so well. So you did something we expect from software to save time. I'm allowed to mention that this is one of our sponsor talks, AEC.
Yes.
And we have time for one question.
Hello, Nick. I am Gonzalo from La Salle University. I'm afraid I have a similar question that the one I raised before. We are talking about race that have 10 years. So my question is the industry using race right now? Because you presented this tool, but to one extent this tool can be used by the industry, and who is the user of this tool? We are talking about a new position in the market, an expert rule?
No, we have not taken it to market. It's a development platform. It's been used in research projects successfully. And across the world, people are using Raise as a way of thinking, even before they get to code. It is a mindset. Those 4 colors actually allow you to read anything and understand it directly. So it's a set of ideas, first of all. And now the software is ready to be used anywhere that it's needed. The problem is that people assume that they have to write software. And so there's a whole mindset. And to be honest, I think Chuck Eastman is probably to blame, because he said there are 4 steps. Step 1, write some software. It's not necessary.
But you, for example, expect that one technician,
it should
a
be
municipality is able to apply this method?
I trained the people at the health and safety executive for 20 minutes, and they nearly got it. If I'd had 40 minutes to train them, I think I would have had a room of senior executives who understood Raise and could do it. Okay. So it's, if you've got 40 minutes, I will teach you.
Okay. Fine, let's do it.
So thanks again, Nick.
Okay, thank you.
And now we go further to the west and ask Bruno Muniz to the stage.
Let me test it. Okay. So, hello everyone. My name is Bruno Muniz. I'm a PhD candidate at the University of Minho. And I'm going to talk about the development of an IFC-based platform prototype for rule editing and code compliance check. So this work was done for my master dissertation at the University of Minho within the ISIS research unit, and also took a lot of inspiration from my work in the check project. So first, I would like to start talking about the challenge of automatic compliance check process, and I'm going to highlight 2 points. First, I'm going to talk about the regulations. They are quite ambiguous, and they have a lot of omissions and several other factors. So, for example, I extracted one clause from a Portuguese regulation, and I'm going just to show it very quickly. We have here said that the technical equipment installed on the roof of buildings must comply with the following requirements, and the requirement B is: in flat roof situations, their volume must be contained within 2 virtual planes of equal inclination that must not exceed 20 degrees. But the thing is, where these planes come from? What is the technical equipment for the scope of this regulation? 20 degrees with what? So we have a lot of information that is needed in order to turn this objective and in order to apply this and implement this automatically. Another factor that I want to address is the scalability. So we have a lot of regulations. We have actually an extensive regulatory framework. And for some municipalities, we have several levels of regulations, and that turns very hard to implement these several regulations. So we have to tackle this in some way. Okay, we have a lot of methods and technologies so far to help us to address these challenges. And here we have the RACE that helps us extract information from the natural language of the regulations. We have the BETTER, for example, a language, a domain-specific language that enables us to work with BIM models, and also a visual programming language that makes it easier for non-coders to start working with these regulations and coding rules. So our work was to look into all of these methods and technology and set some cornerstones that you can see here in order to create this platform prototype. A platform prototype that is capable not only of creating the rules, but also to check the models based on those rules. Also, I would like to point out that it was made within an open source framework. And also we wanted to use the rules created based on local permitting concepts. So instead of working directly into the model, we wanted to create rules based on concepts such as parcels, such as alignments, that would make easier for the technician in the municipality to know what they are coding for. So for that, we were capable to do that by creating a high-level model. This model was conceptualized based on a work that we have done on several clauses of the Portuguese regulation. And with that, we extracted the entities and the objects that are needed to execute these verifications, and we implemented this into a series of classes using Python. And also some tools such as the IFC OpenShell and TrueMesh that enable us to map these concepts and these entities, these classes in Python, to the model using also processing of the geometry. And with that, we could work inside Python, not using the IFC classes, but instead using the concepts of the regulations. So actually, after the implementation of the model was quite straightforward to create the visual programming language. We have used the Blockly library, which is a library developed by Google to enable us to create the visual programming language and also to generate the code that we wanted with this visual programming language. So actually, we developed a series of blocks that are based on these concepts that we were able to extract, and several other auxiliary blocks to enable the development of the logic, of the rules, and also the connections, comparisons, and so on. Also, going behind, we have all of the connection between the front end and the back end of our application that is done by a REST API. So I could say that we have this machine interpretable format, which is in the JSON format that has the Python code that we create using the Blockly language, that it is incorporated within this JSON format and enable us to pass this information to the backend where everything is processed and is returned also with the REST API to the front end, where we can show in a web viewer all the results of the verification. Here then I'm going to show a video of everything working as it is right now. So first we can create a digital regulation, which will be this box of the rules that we can create. We have some information here. Then we can use the visual programming language to create several rules using those blocks that we make available. You can see that here in the right panel, the Python code is generated simultaneously using these objects and this model that we have implemented. We might say that these blocks can be rearranged to code several different other clauses. And you can see here some different clauses. Then we can create new checking records, so we can connect the IFC to several regulations that we want to check, and then we can send this to execute at the backend, and all information about the model will be executed and returned in the format of a report where we can check the series and groups of objects that are compliant or not. So this is very simple, and we wanted to do this very simple. We found some challenges in the process, and we are going to emphasize this. So we have tried to use the geometry processing to try to map these concepts, these abstract concepts of the permitting process to the FC model. And we think that is a right way for a lot of cases, but this implies a very heavy challenge in some cases, and we thought that this should be further investigated. Also, the mapping to FC, because sometimes, a lot of times actually, we won't find a relation one-to-one to a permitting entity and IFC entity, so we have to find another ways to do this mapping, and classification systems could be a good way to do that. Also, the regulatory framework, because for us, it was clear that we would need to rethink some of the clauses and the regulations that we have in order to think not only not about the 2D-based regulations that we have right now, but how we could verify and establish requirements for the urban planning with all of these new tools and new ways to portray the information that we have right now. So the conclusions are mainly that, okay, we have developed this, and we are capable to create this platform that are accessible to non-coders. So hopefully technicians can create new rules, manage, edit new rules. The implementation of local permitting concepts in a high-level model brings the rule creation even closer. So we really wanted to make available the concepts in a way that they can code with the concepts that are in their regulatory framework. The expansion of classification systems, as I said earlier, is a way to map in a more efficient way those concepts with the IFC model. Execute verifications based on geometry processing also can make everything more consistent sometimes, but also is a big challenge. And the way towards a more automatic compliance check process involved the update of the regulatory framework. So it was basically that.
Thank you, Bruno. Do we have any questions? Yes.
Thank you. Jesus Cerezo, Madrid Municipality. Okay. Can you explain more in depth, please, what you have said about including rules inside the JSON in natural language or the formula code?
No. Then I have the editor that enables us to create the rules using the block language. So behind the block language generate Python code, and then this Python code is stored in the JSON format. So the person that is creating the rules do not mess up with JSON, Python, or wherever. They just think about the blocks that are available for them to create the rules, and then everything goes behind automatically. Yeah.
Thank you. Do we have another question? Yes.
Is it available for us to try it or to
Yeah, I'm just Dockerizing it,
or?
And I think that it should be available to work with it.
So thank you. So then, Bruno, thanks again. And as in the first session, it was Bruno's first talk in English. Okay. So you did a really great job. Thanks a lot. And since we started to go west, now we go far, far southwest, and we welcome Bruno Rienzi from Uruguay.
Hi, I'm Bruno Rienzi from Universidad de la República in Uruguay. I'm joined today by Raquel Sosa and Laura González, and I'm presenting this work that was proof of concept that was carried away by a group of students. That's why you see so many names there. And this is an approach to work with GeoBIM. GeoBIM is the integration of GIS and BIM, so we can solve problems that need information from both worlds. And we can do this because they share the spatial dimension. In many of the works that we studied, GeoBIM was implemented by model transformation. For instance, the IFC file was transformed into a CTGML file. To give you some background, in 2023, we worked on an open DBP platform for the city of Montevideo, which is the capital city of Uruguay. And we had different regulations. Some were municipal regulations, some were national regulations. And in some of the requirements coming from those regulations, we had to use not only the intrinsic data from the IFC file, but also some context data, for instance, from a geometric layer to calculate the maximum floor area ratio, for instance. So we saw the need to integrate a GIS system into our solution. That was not implemented finally, but we wanted to test some more advanced approaches. This is the overview of the OpenDBP platform that I was talking about. If you want to delve deeper into it, you can stay tuned because Laura will talk about it tomorrow. I will just mention in this platform we have the AEC applicants who submit an IFC file. Then the platform checks some requirements, a subset from the regulations that I mentioned. And if some issues are found, they are reported back to the applicant. Okay. In this platform, we work only with files, IFC files, BCF files. But being computer engineers, as we are, we don't like files that much. We prefer databases. So we wanted to try a different solution, and that's why we proposed this proof of concept to a group of students, undergraduate students of computer engineering. They implemented a prototype. That's the architecture of that prototype. This has a middleware module that was implemented in Python. And we didn't want to perform a model transformation because we wanted to try a different approach to that. Usually model transformations are done with ETL tools. So we wanted to keep each model separated. We have two different sources, one for the BIM models and one for the GIS models, in this case, the city models. And we extract the information that we need to make a calculation. We do it with a GeoCalc module. We do that in memory. We used several Python libraries like SymPy for mesh geometries and Shapely for spatial operations and PsychoPG to access the databases. And as you can see, we used two providers. One is the 3D CTDB. That's a database that runs with, it's an extension actually that runs with PostgreSQL and Oracle, etc. And BIMServer that has the IFC information. And so we query those sources and perform calculations that need data from both of them. So the first step was we had data in file formats. So the first step was to import that data into BIMServer or 3D CityDB. And from that moment on, we can go on working with services and database queries. Okay, this is a very simple city GML model that we used. Basically, we have a city block, which is divided into parcels, and we construct what we call a maximum bounding volume. And the height of that volume is the maximum allowed construction height. Then we borrowed some test data from the OpenDBP platform, two simple houses, A and C, that have to be georeferenced to work with the city block information that we have. Those houses, those BIM models will be depicted in the next slides as a green box, like that one. And this is a summary of the calculations that we performed with the software module. First, we had to identify in which parcel that building is going to be sited. So we can do some spatial operations to find the answer. In that case, we found that it is parcel number 9, ID 9. Then we can calculate the floor area ratio, a distance between the maximum allowed construction height and the height of the BIM model that we have, and also the setbacks, that is the distance from some face to the property line. Those were the calculations that we performed with this module. And these calculations can be then used. We did do that with this proof of concept, but then they can feed the platform, for instance, to perform some rule checking and so on. So to wrap it up, we confirmed the technical feasibility of this approach, that is to integrate information without doing a model transformation, and also to use some products like BIMServer and 3D CityDB that are not widely used right now, but we believe that in the future, as has happened before with vector data, for instance, database and service-based solutions will be more widely adopted. So maybe our conclusion is that those tools are not yet ready for prime time, but they are close to that, especially 3D CityDB. And also, we concluded that some regulations can be verified with this approach. For instance, when we want to test the satisfaction of the floor area ratio. And for future work, we still have to decide or be able to decide when we really need to do an entire model transformation, and when we don't need it. We still don't know. We just try for some simple cases that it was not needed, but for some other requirements, model transformation can make sense. So it would be interesting to know when we can follow one approach and when we can follow the other one. So thank you very much for your attention.
Thank you, Bruno. Do we have one question? Yes. So, Jan.
Thank you for the presentation. I fully agree that the database and services are the future. But we already did that for Estonia using BIMServer for prototype back in 2019, and now it's as a live system using BIMWorks running in the Estonian building permitting process as well. So I was just wondering, are you aware of the work done in Estonia as well regarding the BIMServer and?
No, I was not aware of that. Is that in production right now?
Yes, it's in production.
Okay.
So and yeah, Future Insight, one of the sponsors, is actually has made a product out of it. So it's already on the market. So just wanted to let you guys know. Thanks.
Okay, thank you.
So thank you, Jan. Another question? So then thank you again, Bruno.
Okay.
And this shows one important part, that we connect information together and then we work better. And even if it seems impossible, we still can go farther to the west and welcome from New Zealand, Robert Amor. So the stage is yours.
So I'm not sure if it's west, north, south, east. We're on the opposite side of the world. So whichever way you go, you'll get to New Zealand. So from the other side of the world, I want to talk about an implementation that we've made. So been working for over a decade on developing solutions for automatic code compliance checking, and got to the point of deciding that we should really put our money where our mouth is and develop something that could do this. So this is where we've got to. I'll show a demonstration of it. So the ACABIM tool that we've talked about in research for over a decade, it's an open solution. So we believe that everything should be an open format. So speaking to this, how do you make things available in 50 years' time? Well, we take the model in from IFC, open solution. We take the checklists, the approach for looking at how you perform, checking of regulations from the councils. We take that in an open BPMN format, and the codes and regulations that we have, we take again in another open format, which is Legal Rule ML. So all of those open sources come together through our rule checking engine and give an audit of the building in the same way that our councils, building consenting authorities, would normally do if they were doing that. We know we can't do everything together with computers, although programmers are going to be necessary. I'm a computer scientist. You'll never get rid of programmers. They've been saying that for decades. So human input, very, very necessary. And so our process allows for calling out for humans to provide input, also allows us to get to simulations. We've been testing this with Christchurch City Council, one of the largest councils in New Zealand. And, God, it's problematic. BIM models are crap. We have never, ever seen a BIM model which complies, which has all the information that's needed, even though the council publishes the requirements for it. No matter who the architect or engineer is, they just can't give you the right information. So Tanya and others, we need that semantic enrichment. We need it now. There has to be other approaches to fix BIM models. I don't think humans are going to be able to generate it properly for us. As I say, the councils have the current approach of checklists, so we are using the checklists that they have, turning them into a process and doing checking, generating the functions which are needed for that, and we have a whole set of procedures which are defined. Man, we wish these procedures were in IFC, so there was some standardization of how you calculate areas and all of these other things that everyone in the world has to do. Languages that Andre and others have been putting together, really, really necessary for us to be able to do the checking that we need to do of the IFC models that we have. Translated codes in New Zealand. So 15 of the codes that Christchurch City Council said were their priority codes. This is where they put the majority of their effort when they're doing the checking. So we've translated those. These are acceptable solutions. So this is the prescriptive form of our performance-based codes, so they are much, much easier to check. In the 2 years since we put those codes together, 5 of them have changed, 3 of them have merged, 1 of them has disappeared. So this question of how do you keep up, who owns these codes and how do you maintain them is a really, really big question for all of us as we try and do this work. And then I have from our partner a demonstration, and if our technicians are happy to run the demonstration. And hopefully there's audio.
6 different solutions for different phases of a project lifecycle, from land development, planning, design, construction, operation, and retrofit. Let's take a look at how the compliance checking process works during the design stage. First, select a project with IFC model to work with. Once the project is selected, you can look at various details of the building, including its embodied carbon. You can view the building models and look at various properties. This is a single-story residential building in the city of Christchurch, New Zealand. Let's take a look at a few compliance checking scenarios. Let's check the building for compliance by selecting a CAP. A CAP is BPMN compliant workflows that can query BIM data and legal documents in Legal Rule ML. This particular CAP can be used to check if the vertical clearance of extractor hood above a cooker in a kitchen complies with regulatory requirements. The result is an OK in this case. Let's change some building parameters and see the impact on compliance. Changing the space function has the impact on the type of activity in that space, as well as the number of people that is likely to be in the space. Let's re-execute the CAP to see the impact. As we change the function of the only kitchen in the building to be an office, this results in no kitchen found in the building. Let's look at a few more scenarios. We can change some of the user-defined properties such as cooker fuel type and extractor type. Let's re-execute the CAP to see the impact. We just changed the cooker type from gas to electric. The outcome of the check is no gas cooker found. Further check may be required for electric cooker. Let's change the cooker fuel type back to gas. And let's change the extractor type to just a fan. Let's re-execute the CAP to see the impact. This results in non-compliance. Let's change the cooker fuel type back to gas and the extractor type back to range hood, but also change the installation height of the extractor. Let's re-execute the CAP to see the impact. This results in non-compliance, as the vertical clearance is now less than the required threshold. Multiple CAPs can be executed together in a batch. Depending on the complexity of the checks, it may take a while for the process to be completed. Let's look at another example. This is a 6-story public library building in the city of Christchurch, New Zealand. In this exercise, we are going to check the building for compliance with accessibility provisions. There are several things to check, including minimum width of accessible routes, minimum capacity of stairs, and means of escape from occupied spaces. A few violations found. One of the corridors has less than the minimum required width. One of the stairs has steps with the riser height exceeding the required threshold. Note that these violations are marginal and would be considered okay. Another violation is one of the spaces has less than the required number of doors. In this case, 2 doors are required to comply with the means of escape provisions, but only one is provided in the design. Let's look at another example. This is a reasonable large 2-story commercial building in the Auckland city of New Zealand. In this example, we want to know if a lift is required in the given building. The regulatory provisions have several parameters to determine if a lift is required. This includes the use of the building, the number of story, and the number of occupants. In this case, the outcome of the check is that a lift is required given that the number of occupants on the upper level of the building exceeds the threshold for the type of occupancy. Let's look at another building model for the same type of check. This is a single-story residential building in the city of Christchurch, New Zealand. The outcome is that a lift is not required as the building is a single story. Now, let's look at how we can support compliance checking of performance-based requirements. Let's say we want to check the compliance with the means of escape from fire, which is to ensure all occupants can get out of the building in the event of a fire. This could be achieved by generating an input data for the industry standard fire simulation application FDS. We also execute the appropriate CAP to generate the required input data. This CAP extracts the building geometry and spatial relationships for the purposes of FDS simulations. The generated simulation input data can then be exported to the FDS simulation tool. Subsequently, the outcome of the simulation can be fed back into the CAP. This results in a compliance solution for the project. A PDF report on the compliance checking outcome can be generated if desired. ACABIM is developed by CAS Limited, based in New Zealand.
Okay, so just some very simple checks being shown there. Just to give you an idea of what's there, we roll them all together and we can check a particular code, the complete code, if we need to. And as I say, this is a tool that hopefully will work for New Zealand's requirements and anywhere else in the world where you have open specification of your rules and regulations and your processes.
So thank you again. Do we have one question? There's one in the back. So I'm now coming also to 10,000 steps.
Yeah, hi, hello, I'm Gazbin from INS. I have a question in regards of maintaining the rules which are the part of your compliance check. How are you handling the upgrades and changes that the regulations are actually imposing on you?
We're trying not to. So we believe the rules and regulations should be maintained by the regulatory body, not by a software development company. So in New Zealand, we're trying to have the standards specifier holding those rules and updating the rules as they change their regulations. So you know, our tool pulls the rules from a database, and if as they make changes, we can pull the new codes, the new specifications in, and apply the new values that they have from the rules and codes. So yeah, we don't want to touch regulations.
But in case like the governmental body decides to add new rules out of any reason, how does this change happen in your system?
Yeah, so again, this is where we work with the councils. So as they adapt to the new codes and regulations, they have a new checklist to be able to interpret those regulations. Then we update the BPMN flow to have that checklist inside that flow and call the right part of the regulation to pull that out. Okay. So the BPMN checklist is the thing which is actually driving everything there, and that's how the councils, the compliance auditors now interpret our national regulations and apply them, and that's where everything is run from.
Okay, thank you.
Thank you. It's actually an approach we also try in Austria, that the regulators provide the coding for the regulations.
Yeah, it'd be really nice if they would, eh?
Yeah, that's true. So, thanks again for your talk. When I look in the audience, then I see a group who is in desperate need of a lunch and to chat and go in depth talks. But before we have the lunch, we go up to the terrace to have a group photo, and then lunch is ready for you all.
Sorry, blah, 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 blah. Blah.